So this is lecture 12 and the last lecture of the 2023 NITheCS SATACS course in category theory. What we're going to do today is a bit more of proving things in categories. This time we're going to be working in something that's called a pointed category. This kind of takes us back to our first couple of lectures where we were talking about the category of matrices and the phenomenon of coincidence of binary products and sums. And we might have also mentioned then that in some categories, like the category of matrices or vector spaces, the initial object and the terminal object coincide. So in any category, if there's an initial object and there's a terminal object, then there will also be an arrow from the initial object to the terminal object by the universal property of either of them. And now we require this arrow to be an isomorphism. And when this is the case, these objects are called zero objects. The examples where this is the case include the category of monoids, the category of groups, the category of abelian groups, the category of vector spaces and generalizing class 2, category of R modules for a ring R, and others. In fact, funny enough, it turns out that even the category of sets with relations between them is a pointed category. Sets where morphisms are relations, not functions, but relations. And the reason for that is that then the zero object there is the empty set, and for any other set, you've got unique relation in each direction. So it's both initial and terminal. Does that make sense to you, Alexander, what I said just now?
Yep, I know what relations are.
Okay, fantastic. There are semigroups here. Semigroups, no, because in a semigroup we don't have identity element. And because of that, the initial object in the category of semigroup is actually the empty set, whereas the terminal object is the singleton. And so they differ. But because in monoids we have identity elements, sort of better. What we're going to talk about today will be a special property of a category that is shared by all of the examples that I listed in here, and if I'm not mistaken, also this one. So it's a very, very common property.
Sorry, I have a question.
Yes.
Does it hold for fields as well if we assume that they have the same characteristic?
Well, field theorists, or at least those who apply fields in their work, do not like to think of a singleton as a field. They like to insist that in a field, 0 and 1 must be different to each other.
At least two elements, I know.
Yeah.
But
if
take
we do that,
object. Yep.
if we do that, then there is no terminal object in the category of fields. Because with that restriction, then every field homomorphism is going to be injective function, and terminal object would be a field that contains all the other fields in it.
Oh, all right.
I think it will be too large. It will be an object that will be too large. So, no, but it should also contain it uniquely. So I think it should be possible to prove quite easily that there is no terminal object. Neither of there are products, by the way. In the category of field, binary products do not exist.
Yep, I know.
And
so we have no problem with initial objects, but terminal objects cause a problem. Okay.
Yes. And what about coproducts? I would guess that there aren't coproducts either in the category of field. It's a very bad category. It's a subcategory of the category of rings. The category of rings is wonderful. If we do allow 0 to be equal to 1 in a ring, then it is a category No, well, if it's rings with identity, then initial object there are integers and not the zero ring. So it's still not pointed. If we consider rings without identity, then it will be a pointed category. And so the category of fields is a very bad subcategory of the category of rings. But it has other nice properties, like every morphism being a monomorphism, for instance, which is very, very special property. Okay, so what is this special property that all of these named categories so far share? It can be written out as a simple isomorphism. A times B divided by A is isomorphic to B. Now, these A and B here, they're not numbers. If they're numbers, then we know this is true. They're mathematical structures. But in order for us to interpret what it means to multiply and divide, I need to be inside a category of structures where we have notion of product and quotient. But furthermore, in order for us to be able to talk about a morphism that goes from A to A cross B, which will be the thing we will be quotienting out, I need the category to be pointed. Because this morphism, in all the examples mentioned above, will be the morphism that's induced by the universal property of the product by two morphisms. One is the identity morphism, and the other is the zero morphism, which is the morphism that factors to the zero object. So for any two objects A and B, I always have an arrow going from A to the initial object, sorry, to the terminal object, but now it's the same as the initial. Zero object is usually written as a zero, so that's why I wrote it zero. So this is the case for 0 equals 1. So we've got this unique morphism there. And then by initiality, we also have a unique morphism here, which gives rise to a special morphism from A to B called the zero morphism. We'll just denote it by 0. If necessary, we will put subscripts A and B as well. And these two morphisms induce a morphism here, which we'll write as a pair, 1, 0. And it is this morphism that embeds A into the product. Well, there's nothing special about this. We are familiar with such things. If we take vector spaces, for instance, if we take the real line, we can insert it onto the Cartesian plane by this very morphism, which will map x to the x-axis. So to the corresponding point on the x-axis, in other words, point x0. Okay, so now we've got a morphism from A to A cross B, which we call actually iota1. We call it product injection. We have product projection, which are the morphisms defined by the definition of product itself. And in a pointed category, we also have the opposite, a product injection. In order to quotient this out, we need another morphism, because we need, as we know, quotients are captured by coequalizers. So we need to coequalize something, so we need two of them, so we can coequalize them. Now the quotient process, we discussed quotient process last lecture when we were quotienting out an equivalence relation. But if I'm quotienting out not a relation, but a sub-algebra or a substructure, it means that I'm squashing everything to the zero of my structure, right? In a vector space, if I quotient out x-axis, it means that I take all the numbers on the x-axis and I want to stick them to the zero. So which coequalizer should I consider here?
What is the other morphism?
Yeah.
Zero?
Yeah. So, yeah, I will be coequalizing with a zero morphism. And such a coequalizer is called co-kernel. It's because it's dual to kernel.
So can we like really do this, because a zero morphism is from A to B, not from A to A cross B?
So I need the correct one. I need the one that goes from A to A cross B. Thanks. I have one for any two objects because I can always draw this, right? And just let's just remind ourselves that this itself is has a bit of 0 in it, so it's 1a and 0ab. So this will be called the co-kernel of iota 1. Okay, so just to get a bit of an idea what this does, let's perhaps compute it in the category of sets and relations as being morphisms. First of all, let's compute what is A cross B there.
Sorry, I just want to quickly ask the connection between quotient and co-equalizer. Is the co-equalizer as an object what we think of as the quotient?
Well, we actually want to think of the pair consisting of the object and the morphism into it, which is written, the morph is written with small c. So let's look at an example. I've got a set A. Well, first of all, let's see what would be, in this example, what would be product. So I've got a set A, a set B, and I'm looking for a set here in the middle with some binary relations connecting with A and B, so that relations from C to A and from C to B are uniquely determined by relations from C to that object. So this should be something that is able to encode a pair of relations from C to A and C to B. What do you think it should be? The product. Well,
what does C denote here?
any other object in the category of sets and relations. So,
I know it's the
so let's say I have my A has 2 elements and my B has 3 elements. And now let's say I have a relation here from a singleton. So it will relate to one of these to this point, or to nothing, or both, yeah. And the same on the other side.
we can have the string.
Yeah, Carlisle is right there. So it turns out that product is the disjoint union, and it will coincide with the coproduct as well. Because relations we can just reverse, take the opposite relation, and we get opposite universal property. So it turns out that the product in the category of sets and relations as morphisms is just the disjoint union of A and B. And so whatever relation we had on one side, so we had some kind of relation here on this side. We had some kind of relation there. And we will just duplicate those relations in each side to get a total relation from C to A disjoint union B. But what about the product projections? What are they? Because that relation now composed with this projection should recover completely the starting relation from C to A. Do you have an idea, Alexander, what will the product projections be? So let's specialize to a concrete example here. Let's say there are 3 points here and 2 there and 3 there. And let's say the yellow relation relates this with these 2, and it does nothing else. And the green relation relates these 2 with those 2, and maybe another one. So like that. Does nothing else. Then in the middle here, I'm going to have a relation which consists of the yellow piece, which is the same as the other yellow, and the green piece. But now I'm putting the same color on them because now it's seen as a single relation. So what relation should I have from here to there so that that composed with the blue relation gives me the yellow relation? And the same, what relation should I have from here to here so that composed with the blue relation gives me the green relation?
So if it's like the same elements, we can do the same, so to say, not change anything. But if we take elements from B, we have to somehow correspond empty set to it, so to say, no relations.
Yeah. So things from the A copy relate to itself by an identity relation, and things from B copy to B by identity relation, but things from the copy of B copy do not relate at all to anything in the A copy. So that's how the product projections work in this case. Which is something we couldn't have done if these were functions, because then I have to map something in B somewhere. So that's why in the category of sets, disjoint union is no longer a product. Okay, so that's just to have a bit of an intuition behind product. And now that we have such an intuition, let's construct these two maps and let's compute the co-equalizer in the category of relations. So what are the two maps? So first of all, I take the disjoint union. So I'm now trying to model this thing. So I take the disjoint union, A and B. Well, maybe we should also decide what the zero arrows are, these ones. I think we did say that it's the initial object, the zero object. So it's a relation that factorizes through the zero object. So it will be the empty relation. So this relation will be the empty relation. And what about this one? It's a relation that's induced by identity and empty into the product. So it's the situation where the yellow part is identity, the green part is nothing. It's exactly the reverse of this relation, putting A into the A component. Do you agree with that, Alexander?
Yep, totally.
Mm-hmm. So we got this. This insertion is our iota 1. And now we want to compute its co-kernel, in other words, co-equalizer of these two maps. So the other one is the empty one. So let's actually distinguish those by, maybe I'll draw some parallel lines here, whereas in the other one, I'll leave that empty. So these are the two relations. And
This is just
the co-kernel needs to have the property that the two composites are the same, right? So it should be a morphism going out of A, so that when I compose with identity, but not with identity, I mean with this part, it's the same as composing with this part. So whatever was related to something here, it can't get related to anything there, because then if it does, then the same should be on this side, but on this side, this point doesn't go anywhere. So all of the points that come from here must be annihilated by this relation, right? So should it maybe be a relation to the empty set? Well, while everything on here, on this side must be annihilated, things on this side can be anything. Because if I did have some things here, right? The composites would still be equal if this side is annihilated. So empty set is too tiny. It has to be. We get a nice symmetric picture like this. So this relation would be, so we now figured out that the co-equalizer of iota 1 and 0, A cross B, is actually B. But let's actually prove that rigorously. So I want to prove the universal property, right? So if I have a set C with some relation here, such that this relation R composed with iota 1 equals the relation R composed with the empty relation, then I need to get a unique thing here, which makes the triangle commutative.
Can you write iota 1 as a union of two relations and then distribute?
Yes, that's a good idea. We could do that. That's a very good idea, actually. We can write iota 1 as union of the identity relation on A. So set of pairs AA, union with, well, with nothing, right?
Yeah.
So maybe it's not such a good idea. But set theoretically as a relation, it is this object. And now we know that we want this to equal, well, we can compute already here. What will this be?
Empty.
No.
Or composed of
Oh, sorry. Yeah,
oh,
this has to be empty. Yeah, sure,
Yeah.
sure. Sorry. This is the condition we have. It has to be empty. But what I wanted to say is that we can still compute what the left-hand side here is. These are all the pairs of the form AC, right? So these are all the pairs of the form ARC, so all the related pairs, where A comes from this first copy of A. I'm going to write it as A bar. So A bar refers to the A copy in the disjoint union. And so now what we know about R is that that is empty. So we know that no A relates to a C under the relation R. That's what we know. This requirement that this equality holds.
So what is this equality saying?
That's what I wrote here. That's what it's saying. So if these are equal, means that this is equal to that. But now what is this? This is the composite of R with that relation, right? So if I compose them, I'll get, so here is some A. Here is the same A.
Yeah.
And then there is a C.
No, I'm just confused by the AR. It shouldn't be a pair.
Yeah, this is a pair such that I made a shortcut notation here. It's a pair such that, so what I meant here was pairs AC such that ARC. Then I don't need to write A's in A bar anymore. Well, I do. It's not all the A's, such that those that come specifically from A bar. So I'm not doing anything. I'm not saying anything about those A's that come from B. Alexander, are you okay so far?
Yep, so far.
So that's what we know about R. And now we need to produce this unique relation. And if we also look at the picture, we now know for sure that nothing is happening between these two. And whatever happens here, on the other hand, must be the same as whatever happens here, because this part is identity. So that will already prove uniqueness. And also existence, because now we can propose this relation to be iota 2 composed with R. What is iota 2? It's the same as iota 1, but now for B instead of A. So in other words, this is the set of all pairs B, C, where the copy of B inside B bar, which is iota 2 of B. Iota 2 is a relation, but in this case, it's also a function. As we see here, iota is actually a function, coincidentally, is related to C.
Why do we need iota? Because B is just, it's not a disjoint.
Yeah, so if I think of it as the same B living in, it's a disjoint union, that's fine. So this is the B in B bar. So are we convinced of the universal property of this co-kernel?
Sure, yeah.
So once again, so what's the argument? So if I have an R such that this holds, that means that R only relates things from B to C, doesn't relate things from A. Then if I propose this specific relation I wrote here, the diagram will commute because there's nothing related from A to B either. And on this side, as far as this side is concerned, because this identity here, and we used here the same relation as there, the diagram will commute. So that's existence of this arrow. And why is it unique? Well, what other relation could we put there? Because I've got identity here, this relation is forced to be the same as this one.
Yeah. But it's a bit more nuanced than in set with function, because you can have partial inverse to a relation.
Sure, but here, nevertheless, I know that this composed with that must be this. And in particular, it implies that this piece composed with this piece must be this, because there's nothing here.
Yeah.
But then this becomes now, this is the identity morphism in the category of relations. So we are using a bit of diagrams here. Writing this out rigorously would require a bit more than what we wrote. Is also okay with you, Alexander?
As well.
Great. So we've actually proved the claimed property that you see what we proved, that the co-kernel is B. And that's exactly what I wanted to say with this equality. So when I have insertion of A into A cross B thanks to pointedness of the category, by what I mean by this isomorphism is that the co-kernel is isomorphic to B. More precisely, it's not just any isomorphism, but the one that's obtained by the composition of iota 2 and Q. So there is a canonical map from B to this co-equalizer given by composing Q with iota 2. And this condition requires that this canonical map is isomorphic, which is the case here, because that's how indeed we constructed that isomorphism. Now let's look at the category of monoids. Why, or maybe groups, doesn't matter. Why can we expect something like this to be true there? The reasons will be completely different.
So what we have used so far is the existence of products.
We have used in very detail. We've used the specific nature of the category of sets and relations. We've used the fact, for instance, that products are given by disjoint union, which is not true for monoids anymore. Product is the usual Cartesian product there. We've used that because our argument relied strongly that zero maps are empty maps. So let's set this up, the same thing up now in the category of monoids. So these are, just a reminder for anyone watching this video, these are structures x.1, where dot is associative. It's a binary associative operation, and 1 is identity element for that operation. In other words, we can think of these as single object categories. So first of all, in the category of monoids, the zero object is the singleton monoid. It only contains the identity element. Not difficult to see that if I have any other monoid M, I will have unique morphisms back and forth. The forward one will map identity element to the identity element. The backward one will map everything to the identity element. Both of them will be monoid homomorphisms. Do you agree with that, Alexander?
Yep, I do.
We already kind of know from our earlier discussions, if I'm not mistaken, we know from our earlier discussions that products will be just Cartesian product, where operations are defined component-wise. So A cross B, what will be the operation on it? So AB times A prime B prime will be just AA prime BB prime. That's how product is defined in the Cartesian, in the product of two monoids. That's how the binary operation is defined. And it's easy to see it's going to be associative because associativity will reduce to checking that in each component, which are associative since A and B are monoids. And the identity element is just a pair of identity elements. So that's how products are constructed in the category of monoids. The product projections are just projection maps. So if I take this product, A and B, pi1 and pi2 will map the pair AB to A and B respectively. Okay, then what is the iota1 map? So I've got A here, I've got the identity A here, I've got the zero map here, which is the thing that factors to the singleton. So that's clearly a map that maps every A to 1. Here, on the other hand, I've got A mapping to A. And so the induced map here will map every A to the pair A1. Right? So we've got now two maps going from A to A cross B. One is iota1 map, which maps every A to the pair A1. And the other is the map that maps every A to, sorry, I made a pause for a moment because I realized that I want to correct something I said earlier. Going back here, when I said that this canonical map will be the composite, and when I said that we already proved that, we didn't quite prove that. What we proved here rather was that so we hypothesized this to be the co-kernel, right? And then we proved that it is. Yeah. But how do we know that so another way to say what I said here was to claim that the second projection, which is actually the way to for the isomorphism of structures above to be understood. So the second projection is the co-kernel. That is what is isomorphism expresses, that pi2 going from A cross B to B is the co-kernel of iota1 going from A to A cross B. And that's exactly what we proved here, because this map here is indeed pi2. The one that does nothing to A and maps everything in B identically. That's indeed pi2. So we did prove that pi2 is a co-kernel. And to prove that, this canonical map was constructed by composing R with iota 2. Now, if this R happened to be another co-kernel, then of course this canonical map would have been the isomorphism, because co-kernels are always isomorphic to each other. So that's how it links up with what I said about canonical isomorphism. But a much easier way to think about this condition is to say that pi2 is the co-kernel of iota 1. And that's what we're going to prove in monoids as well. So I don't need to know how quotients are constructed in monoids, because I have a candidate that I'm going to prove is the co-kernel. So pi2, I want to prove pi2 is the co-kernel of iota 1. First of all, let's check that the composites are equal. Pi2 maps AB to B. In fact, these composites will be equal in any pointed category, but we can come back to that a bit later. Now, for monoids, the way we can see that is that under one composite, A maps to A1, and then by pi2, this will map to 1. Whereas under the other composite, A maps to 1 in A cross B, which is pair 1, 1. And again, applying pi2 to that will still map to 1. In fact, the fact that this composite is 0 map from A to B is trivial, even in a general category, because that's exactly how this iota 1 was defined. It's the unique map which maps together with pi2 makes the composite 0 map. So we actually already know that. We didn't have to prove it separately from us. Okay, this leaves us to show that, I don't know where to put this thing. Now we show that the universal property, that if there is another one like that, there will be this unique factorization. So let's say I've got another monoid C and a homomorphism F. And I want to prove there is a unique map here that makes the triangle commutative. And I'm going to apply the same technique that worked once, because it might work second time as well. And namely, I'm going to try to prove that that canonical map must be composite of iota with the other one. So I'm going to put that here, F composed with iota 2. And I'm going to now check that this works. So what do we need to check? First of all, we need to check that F composed with iota 2 composed with pi2, which is this composite here, equals F. Secondly, we need to check that this thing is unique such that if H composed with pi2 equals F, that implies that H is the same as F composed with iota 2. So everything is still fine, Alexander?
Yep.
Okay, so these are the two things we need to check, 1 and 2. So let's first check the first one. Maybe let's first check the second one because it's easier. I take element, so I'm assuming this left-hand side equality holds. We're actually going to make use of the fact now that pi2 is surjection, hence an epimorphism, and hence uniqueness of this arrow. Element-wise, this means that if I take H of B, I want to prove it's equal to F of iota 2 of B. And so what can you guess or see what equations should I write here? How can I deduce this to equal? So I'm going to have a series of equalities, eventually leading me to this being equaling to F composed with iota 2 composed with B, which of course would be the same as saying it's equal to F to FB1. Can you see how to complete this series of equations?
B1 or 1B?
It's actually 1b. Thank you.
I think we have one. We should just put 1B at the top as well.
Where at the top?
After there's the first equality. So pi h pi 1b give us h of b.
No, that one is correct.
Yeah, yeah. I'm saying h pi
Oh,
2.
okay,
or
so
1b. Yeah.
we put here h pi 2 1b. Okay, b equals pi 2 1b. We agree on that. But we also, by assumption, h pi equals f, and then we're done. Thank you. Okay. So if at any time anyone doesn't see anything, please do interrupt. So we've now proved that if this is true, then this will be true. Let's prove the first equality.
Like, what does ash denote here again?
So I want to prove, so the second part is the uniqueness of this induced map. So I'm assuming there is another one, calling it H.
Yep.
Assuming that pi 2H is F, and then proving that this H equals to the one I propose. That's how I prove uniqueness of this dashed map.
Yeah, all right.
Yeah, maybe I keep that on the drawing. Okay, so for the first one, we'll have F iota 2 pi 2 of AB. And now I want a chain of equalities, which will bring me down to that equaling F of AB. Any ideas what to do here? Of course, if I just compute the left-hand side, it's going to be F iota 2 of B, which is going to be F 1B. And now I need to somehow prove that F1B equals FAB for any monoid homomorphism. What do I know about F, though? I know something about F, right? What I know about F is that F composed with iota 1 equals F composed with a zero map. So what that means, I know is that F of A1 always equals 1. So F kind of kills the A axis. That's what I know about F. But here I have something slightly different. Now I need to make 1B identical to AB. In usual geometry, this is a natural phenomenon. If this is my A axis and B axis, and if I squash all of this to 0, right, then I'll have these lines squashing as well. And that's exactly what we've got here, 1B and AB. So here's my AB, and that will squash to 1B. It will be forced in linear algebra. Why is this still the case in a general monoid?
Feels like we need to use the properties of a homomorphism, but that seems.
We need to use properties of
unnecessary.
a homomorphism, or we might have to use the property this, and also the operations, the algebraic operations, because for sets this wouldn't be the case. If I squash this piece, it doesn't squash anything outside of that piece. So it's very basic linear algebra we have to do here, which turns out to work for monoids as well, just not just for vector space. And the same argument will be valid for vector spaces, for groups, and all the other examples we mentioned earlier, except for sets and relations, for which the argument was very different. So can anyone see the algebraic manipulation we need to do here? I'll give you a hint. Work backwards. And keep in mind we can use this fact. No, not red is not the right color here. Green, we can use this one. In general, when you have two algebraic expressions and you want to link them up, what do? Don't you try to write one expression, rewrite one expression in such a way it will start to look similar to the other one, or bring in some ingredients of the other one? So whoever is listening to this video, whichever year or century it is, we've got here two very, very strong students in mathematics, and they're struggling. So you might want to pause the video now and try to get it quicker than they can. Thing is that it's an extremely easy argument, but not so easy to see, to find it. Sometimes things that are small and light are the ones that are hardest to find.
I just want to say that that's equal to A times f of 1b, but can't really.
You'd be wrong to say that, doesn't it? I mean, this is, imagine this was a linear map. Would you be able to factor A out?
With it in a monoid, you could.
Oh, a monoid is a. I'm talking about multiplication being the addition of vectors. Maybe that's something that we should remind ourselves. So when we're thinking of these monoids in a multiplicative way, the way it links up with the linear algebra is that we want to think of that multiplication as addition.
Okay.
But in any case, we would still not be able to factor A out because it's not that it's bilinear, it's only linear. So.
Okay.
Alexander, do you have some ideas?
Not at all, to be honest.
So how can we make use of F being a homomorphism? Or the other one? I mean, for the other one, we need this expression FA1 we don't have. That's one thing we need. On the other hand, to make use of the homomorphism property of F, we want to have a product of two things. We want to have a product of two pairs. That's the only way we can make use of this, right? If we have a product of two pairs, then we can apply F to them. And also we want to make use of that. So maybe one of those pairs should be A1. Isn't that a straightforward way of thinking about it?
Yeah. And then the other one should be 1b.
Exactly.
Yeah.
Let's try that. So let's rewrite this as product of, well, first of all, we can decompose A as A times 1 and B as 1 times B, right? And then we can decompose this further as A1 times 1B. And because F is a homomorphism, this is the same as FA1 times F1B. But FA1 is 1. So it's the same as 1 times F1B. And then we're done. You agree with this, Alexander?
Yeah, when I see it now, yeah.
It just it feels, like what I'm struggling with sometimes is I feel like I can't use everything I have from normal mathematics here.
Yeah.
It should work slightly more general, and then sometimes there is a component that you have to use.
Mm.
I'm not sure when.
Well, it was very clear what we can use, right?
Yeah.
Okay, so we've managed to prove the second equality as well, which means that we've proved what we wanted. Namely that pi2 is the co-kernel of iota 1, and therefore we established this isomorphism in the category of monoids. And in all the other examples mentioned here, groups, abelian groups, vector spaces, R modules, each of them will have a suitable operation for which this argument will work. For vector spaces, for instance, this will not be dot, but it will be plus, and instead of 1, we'll have 0.
Can we somehow use the fact that all of those are embedded inside the category of monoids?
That would be more. Yeah, we could try to do an argument like that, but those forgetful functors that forget the structure, they behave well with limits, but not necessarily with colimits. And here we're dealing with a co-equalizer. But algebraic, but still we can use that fact, and algebraically, the manifestation of that is that they have these same operations which will allow us to give us the same argument. We want to now extract the core of this. What's behind this argument? Can we turn this into a theorem in a general category? And that's one of the standard, let's say, type of research questions in categorical algebra that tries to conceptualize algebra using categories. So what we've got here is that we established a theorem. Let's write this down. In the category of monoids, as well as in the category of sets and relations, we have proved that this holds, which, as I said earlier, means something very, very concrete. We've proved that every product projection is a co-kernel of the complementary product injection, by which I mean that pi2 always will be a co-kernel of iota 1. Which, by the way, is the same thing as to say that pi2 is a co-kernel of something, because iota 1 will turn out to be kernel of pi2 in any point of category. And being a co-kernel of its kernel is equivalent to being a co-kernel of anything. But let's come back to that later. So let's keep it the way we've written here. But what I'm asking now is, so there are two questions here. Conceptually, what does this property actually say? Oh, sorry, this should be A, right? what does this question ask? I mean, this is a nice formula, and we are happy to have a pretty formula that we've established. But now we want to understand this fact in such a way that we will feel that it's a very natural property for a category to have. This is a very standard type of a research question in category theory. You know that you've got some property that holds, and you want to first of all understand this property in most natural terms. And the reason why you want this is because once you do that, then you have much better idea on the potential of applications of the property, and also you have a good idea about what exactly you discovered. I mean, imagine you go to a mine and you discover some kind of stone. Of course, the first thing you want to know is to determine what kind of stone it is. Just the fact that
if it is a pretty stone.
Yeah, just the fact that it's pretty is not. Yeah, it has to be pretty, sure, yeah. But just the fact that it's pretty is not enough. But now the second question is, what was special about that mine? Maybe you can come up with a general way of detecting which mines will have those stones. So what is special about monoids? What is the core property of the category of monoids that allows us to prove something like this? In this category that allows us to prove this.
Is it not what you said earlier, that you can always, there's always a morphism from A into the product?
No, that we have in any pointed category.
Oh, okay.
Yeah. By the way, a counterexample to this property is the category of pointed sets. Just to show that the property doesn't always hold. Yeah.
Okay.
Pointed sets is set equipped with just a distinguished element. And morphisms preserve the distinguished element. It's like a monoid without a binary operation. And the reason why there this will not hold is because just the same argument is here. I mean, if I think of these x's as pointed sets and I squash everything here to 0, there's no reason why all the other things should be squashed. So these two questions are one of the standard types of research questions in category theory. And what makes the subject exciting for those who are excited about it, including myself, is that the research questions always try to uncover the fundamentals behind something. So if one does mathematics because one enjoys uncovering fundamental principles, then category theory is definitely one of the most exciting research areas to work in. Okay, so we will first answer the second question, and then we will answer the first one. If I look at this argument, so when the second question is asked in algebraic environments like this one, basically to answer it, what we need to do is to look at the algebraic argument and to see where are we really making use of the monoid property. What makes this argument work in monoids, but without having that ingredient, it wouldn't have worked.
Wait, so does this work in, I'm not sure what the structure is called, but something with identity without associativity?
It doesn't. That's what I said about that. These are pointed sets.
Oh, okay. Well, I mean,
and it doesn't work there. But you meant you have a binary operation and you also have an identity.
Yeah.
Yeah, that you've now answered the question.
Oh, is that what you need?
Yeah. Well, it will turn out that that's what we need. So the core step here is actually the step going from here to here. The fact that we can write AB as A1 times 1B.
But that's only for algebraic.
Yeah.
versions.
But now we will translate this in a categorical language that will be applicable to other things as well, including sets with binary relations. So for the second part, it seems that the core property of monoids that makes the isomorphism work is a categorical property which we don't know yet what it is, but we know what its algebraic shadow is. It's a categorical property, if there is such, if we can find such.
It's interesting that you call this the algebraic shadow, because I think of the categorical property as the shadow of the algebraic one.
Well, the thing is that when an object casts a shadow, depending on the angle, the shape will be different. And when we will discover the categorical property, we will see that for sets with relations, it translates to something completely different. So with different shapes having the same common. If we can find such, so it's a categorical property if we can find such that abstracts the following feature, that A times 1 equals A, or rather, let me write it all together. So AB equals A1 times 1B. Imagine we have this. If we have this in an algebraic setting, then we can go from here to there. And after that, we don't use any specific information about the category. After that, I just use the fact that I was given. This is 1. Oh, we also want 1 times that to be same as that, but that we will have for free if we have this, because it subsumes that A is equal to A times 1. So in other words, A equals A times 1, and B equals 1 times B. Now, remember that A1 and B1 are not just arbitrary random elements of A cross B. They are elements that come from iota 1 and iota 2, right? And now we're saying that, I mean, this property kind of says that any element in A cross B can be reached by these two. Any element can be decomposed into these two. Imagine I had a sub. Sorry? Yeah, so like.
There's a unique factorization through A and B.
Yeah, there's some kind of factorization going on here. Imagine I had a monomorphism into A cross B, which algebraically would correspond to some subalgebra of A cross B. And imagine that iota 1 factors through it, and iota 2 factors through it. Imagine I had all of that. What would that mean? That would mean that as a set, if I think of R as a subset of A cross B, it would contain all elements of, I mean, this factorization, the first one, would tell me that it contains all elements of the form A1. So A1 is always in R. And the second one will tell me that B is always in R, right?
Yeah.
But then I would be able to know by multiplying these two that AB is always in R, which would tell me that R is the entire AB. So it seems that our property that we're looking for is that this should imply that this map R is an isomorphism. Now
so
we,
the existence of the factorization should imply that.
yeah, the existence of iota 1 and iota 2. Well, I shouldn't call this iota 1 and iota 2. Maybe I should call them like primes. Let me actually call them a different name. I1 and I2. The existence of I1 and I2 should be sufficient to conclude that R is an isomorphism. Alexander, are you okay with that?
Yep, so far.
Okay, so with this last lecture, I'm also kind of showing you a little bit, very little bit of process of research in category theory as far as it deals with these kinds of questions we're dealing with now. So I had this question of finding a core property of the category, right, that captures this property, the isomorphism. I took the algebraic core property and I tried to abstract it to the level of general categories. And now I want to test my abstraction. Will I be able to use this property to prove that this holds in a general category, in a general pointed category? So let's call this property something. In fact, there is already a name for this. Pointed categories having finite limits, which means having products, binary products, and pullbacks. When the category is pointed, when it has a terminal object, to say that it has pullbacks actually is sufficient to conclude everything else. Which is the same as to say that it has limits of diagrams that are finite. Pointed categories having pullbacks and satisfying this condition are called unital. Coming from the idea that, as you said before, that you recognize, Carlisle, before, that it's the unit, the existence of this identity element that makes things work. And these special class of categories were introduced by Dominic Bourne, who is one of the senior and most important categorical algebraists, and since a long time ago. So this concept was introduced in around 1990. Okay, so we're now going to prove that in a unital category, we've got that isomorphism that we are working with. Taking some time to enlarge the screen. So here's our conjecture. In a unital category, A cross B quotient by A is isomorphic to B. And as before, we set up the diagram. So we've got iota 1, we've got the zero map from A to A cross B. And as we already clarified, this isomorphism means that pi 2 is a cokernel of iota 1, so we try to prove that. Okay. So first we need to prove that pi 2 composed with iota 1 equals pi 2 composed with 0. But that, we said, is already something already familiar to us, because iota 1 is map induced by identity and zero map. And so taking second projection of that will be the zero map This one is the other zero map. And now we just have to prove that this zero map equals to this other one. Well, to a zero map composed with pi 2. But the thing is that zero map composed with any map is always zero map. Why? Because zero map is the one that factors to the zero object, right? So here I have my zero map from A to A cross B, and if I compose it with pi2, it will still factor through that zero object, so it will be exactly that one. Alexander, do you agree with that?
I think yeah.
So we've got here this composite and then pi2, but this composite is the same as that because this is an initial object. And so this whole thing, which is that, becomes that thing, which is exactly that. Is that good? Should I go over it again?
This is all because of the uniqueness of maps into and out of the
Yeah.
terminal.
Can you please like repeat it once?
Yeah. So if I have two objects x and y, zero xy is always defined as the unique map that factors to the zero object. Are you good with that?
Yep.
It's unique because there is, once I fix a zero object, it's unique. The map is unique because there is only one map this way and only one map that way. So there's only one map this way because this is terminal object, and there's only one map that way because it's initial. Okay, now we have pi2 composed with that. What is 0, A, comma, A cross B? That's this map, this composite, right? Pi2 composed with that will be this composite. So we get 0,
So
A, B.
it will be again zero map.
Yeah.
Right.
One thing we do need to check is that this definition of zero map is not dependent on the choice of the zero object, but that's easy to check because if I had another factorization, because both of them are zero objects, they'll be isomorphic to each other. But moreover, this composite will equal that, since again this is terminal, and that composite will equal that because it's initial. So there will be isomorphism that will stick this with that and that with that. So this notation doesn't depend on the specific zero object we choose. Okay. So I'm going back here. So we know that that equality holds, which means that what remains to show is what, as like before, that if I have an f such that f composed with iota 1 equals 0, then I want to prove that there exists unique h. And just like before, we're going to propose this h to be composite of f with iota 1. And just like before, I need to prove two things. First, that f composed with iota 1 composed with pi2, so in other words, this composite, equals f. Was that this first one or the second one before? Let me check. Yeah, that was the first one. And the second thing I want to prove is that if there is an h, if there is another h, such that h composed with pi2 equals f, then h will equal f composed with iota 1, because that's how I prove uniqueness. So you agree with this, Alexander, that these are the two things we need to prove about f?
Yeah.
Okay. So let's first try to prove the first one, which is equality of two arrows. Now, both of these arrows, f, both the arrow f and the other one, are arrows from A cross B to C, right? But the other arrow is also an arrow from there to there. I want to make use of the fact that my category is unital, just like before, I had to make use of the fact that this equations hold, right? And just like the hint I gave you here, when you want to make use of something, you want to reduce your given thing into the language of the thing that you have at that assumption, right? So we have this diagram that defines a unital category. And now I want to prove something like this. In order to apply this property, I would have to incorporate these ingredients in my other diagram. And specifically, I would have to find a suitable R for which we can apply the unital property. So let's draw this R in. We don't know yet what it will be, but let's first draw it in, and then we'll decide what the best thing R should be so that we can make you can utilize that. So we were looking for some R through which iota 1 will factor, and through which pi 2 will iota 2 will factor. So we want R such that iota 1 and iota 2 factors through that. Moreover, the fact that R is an isomorphism implies that these things are equal. So we're looking for a map into A cross B whose isomorphism detects equality of the two morphisms, which would be a map into the domain whose that mapping yeah. Well, if this was identity, yes, it would. But now this map should be designed out of these two in such a way that it characterizes whether these two are equal or not.
Oh, so we're still trying to prove one first.
Yeah. We're trying to match the unital diagram into this one so that we can make use of the property of the category in unital.
But for one, did we not? It wasn't for one that we had that long algebraic proof.
Yes, but now we decided that we abstracted that algebraic step in this step. So we now want to test whether our abstraction will work.
Yeah, but I'm just trying to remember what we did for one in the previous case.
That was the place where we used that algebraic argument.
Oh, I see it.
Which we're now replacing with a diagrammatic argument.
We have to find R and small r.
We have to find this morphism, yes. So we need to create a morphism out of a diagram of morphisms. Does it not look familiar?
It's like maybe an
Equalizer. If this R is an equalizer of these two maps, and the equalizer turns out to be an isomorphism, then isomorphism composed with the two must be equal, but because it's an isomorphism, by cancellation, these two will be equal. So we're going to take here R to be the equalizer.
How do we know this exists?
We have a category which has pullbacks and is pointed, so we'll have to prove that it exists first. But let's first assume it exists, and then we'll try to see how we can prove that. Equalizer of F and F composed with iota 1 composed with pi 2. That's going to be our R. And let's make a side remark. We still need to prove equalizers exist. I did say that all limits of finite diagrams will exist, but we haven't proved it, so still need to prove that. In fact, we even need to maybe prove that products exist. First of all, I mean, this isomorphism probably assumes that products must exist, or we could have interpreted it as saying that if the product exists, then so and so. Okay, so let's keep that as a side note. We need to still prove this. So we pick this equalizer, right, of F and the other composite, and that's our R, right? And now we want these dotted arrows, this one and the other one.
We already have.
to have a dotted arrow into the equalizer, we need what? We need these two composites to be the same, so that by universal property of the equalizer, this will come up. And we also want these two composites to be the same, so that again, that will come up.
Wait, which two composites?
So of iota 1 and these two, if iota 1 composed with these two are equal to each other, then by universal property of the equalizer, there will be a dashed arrow here. And similarly, if iota 2 composed with these two are equal to each other, then by universal property, there will be this dashed arrow making, which composed with r gives me iota 2. Do you agree with that, Alexander?
Yep, I see how it works.
So now let's check that those composites are indeed equal. So F composed with iota 1 needs to equal F composed with iota 1 composed with pi 2.
Supposed to iota 1 again.
Yeah, composed with iota 1 again. But just a moment, isn't F composed with iota 1 zero-morphism?
Yes.
And then this one will be zero composed with something. But doesn't really matter what that is. In fact, that's going to be an identity. No, it's going to be actually zero, right?
Yeah.
The other one too, as well. We already know this composite is zero. So both of them are zero. So that's fine.
And then by the previous thing, they're the same zero.
Yeah, they're the same zero because they go from between the same two objects. So we've checked this dotted arrow exists. Do you agree with that, Alexander?
Yep, I saw that null morphism.
Now the second thing we need to see. So we now want iota 2 composed with those two things to be the same. There is a mistake here, right? This is not iota 1. Yeah, this is iota, sorry. We might change our computation. So this should be iota 2.
But no, okay. The previous one still works because
yeah.
pi 2 iota.
So the reason why this works is a bit different now. So we've got iota 1. Okay, this should be iota 2. So right. Okay. So this is still zero, right? That's how it works, right?
Yeah.
Now for the second set. So this shows the existence of that one there, of this dashed arrow here. And now for the other one, use a different color. F composed with iota 2 needs to equal to F composed with iota 2 composed with pi 2 composed with iota 2. Well, what is pi 2 composed with iota 2? Remember, iota 2 is a map induced by 0 and identity. Yeah. And so this is just identities right inside here. So they're equal, which then takes care of this dashed arrow.
So then R is
R is a monomorphism because it's an equalizer. Every equalizer is a monomorphism. And then by the fact that the category is unital, R must be an isomorphism. So now we know that R is an isomorphism. Since the category is unital, R is an iso. And what did we know about R? It was an equalizer of the two. So we knew that F composed with R equals F composed with iota 2 composed with pi 2 composed with R, right? But because R is an iso, I can further compose these with inverses of R, right? which on one end it will give me f, and on the other end it will give me f composed with iota 2 composed with pi 2. And so I get the equality I want, f equals that. So we have proved that f iota 2, I mean, we have proved basically the first property. Now the second property will follow from the fact that pi 2 actually has a section. So that's an easy one, the second one. So I take this and compose both sides with iota 2. H composed with pi 2 composed with iota 2 will equal f composed with iota 2. If this holds, then that, yeah, if this holds, then that holds. So we proved number one, which means we proved the existence of this arrow. Now we want a uniqueness, right? If there is another h, it must equal to this. So we assume there is another h with h that make with pi 2 gives me f. And we want to conclude this from there. That h actually is this map. And again, there's a mistake here.
And then is it not just the same? Pi 2 iota 2 is identity.
Yeah, this part is identity, and so it gives me that. Are you okay with that, Alexander? Sorry, not this part, but this part, right? So this implies H composed with identity of B. Iota 2 is the morphism induced by 0 and identity, and this is pi 2, so it takes out the identity. Let me know, Alexander, which place was unclear.
So how do we get the last implication?
Because on the left side I have identity, I have H, and yeah, I forgot to complete. So this composite equals that. So
Yeah,
pi,
actually that's the one I wanted to know.
yeah, so pi 2 iota 2 equals identity. That's the same thing what we said here.
Okay.
Yeah.
Mm-hmm.
Okay, so we've now managed to prove what we wanted to prove, except that we made use of the existence of equalizers. So we still want to know they exist, knowing that category has pullbacks and is pointed. And once we do that, then we're done. We've then been able to answer question 2. So I'm actually going to, I'm thinking now whether I should leave that as an exercise or not.
Prove the existence of equalizers.
Yeah,
If there's something else interesting to do that.
yeah, because I also want to answer question 1.
Just a quick question: is every category with this quotient cancelling thing unital?
You mean the other way around?
Yeah.
No,
So it's
this
not.
property is weaker
it's a bit
than
too
being
strong.
unital.
Oh, okay. Wait,
Is that what you asked?
no, I'm asking is it? Oh yeah, yeah. So,
Yeah.
So unital's weak, they're stronger than having this property.
We show that if in a unital category, just summarizing what we showed, equalizers exist, then this property holds. But in a unital category, equalizers do exist. And this is how we can prove their existence. So let's say I've got two morphisms, F and G. Let me use X and Y. And I want to build their equalizer. First, I need to know how to build products. And that's easy. If I take a pullback of the unique morphism into the terminal object, which in my case is the zero object, this pullback is actually going to be the Cartesian product, because remember the definition of pullback says this diagram should commute, but that's for free because this is terminal. And then the universal property is the same property for the product, because again, any F and G will make this outer thing commute because this is terminal. So products can be obtained as pullbacks of things into the zero object. So basically pullbacks of zero morphisms, specific ones. And once I know that products exist, then I can get the equalizer by the following pullback. I'll take y cross y, y, identity. And here I'll take mapping just by F and G. This pullback which I know exists because it's a unital category. This pullback will have Fg composed with P1 equals identity composed with P2. But the left side is just the pair Fp1, Gp1. The right side is the pair P2, So I get that Fp1 equals P2 and Gp1 equals P2. So I get that Fp1 and Gp1 are the same.
So P1 is the equalizer.
Yeah. And more, and if I have now an object, so this is P and P1, and if I've got an object C such that FC equals GC, then I can factorize it there by taking this FC that's equal to GC. And then this will commute, because this composed with that will just observe this in each coordinate here. And then there will be unique morphism here, and this unique morphism will be the one that I'm looking for here. It's a sketch of the proof. So it left as an exercise to check all the details yourself. It would be good.
So where did you use the fact that it's unital?
No, we didn't. We just used the fact that pullbacks exist and it's a pointed category. So in fact, that's a good remark. But in any, let's say that in any pointed category.
Sorry, how do we know again pullbacks exist? Is the condition for unital categories?
Yes,
or
yes. The definition of unital was this property together with existence of pullbacks.
okay.
You need these limits in order for this property to be agile enough to apply in various situations, like we saw now. Okay, so we've answered the first question, or the second one. So let's recall the two questions we had. So we wanted to conceptually understand what does this mean. And the second question was that we wanted to understand what does it mean, what is the property of monoids that makes this work? And we've answered the second question, and the answer is it's the property of being unital. And if I go back now to the category of relations, I can see that even there the property holds, and that also explains why it holds there. Why? So remember that for relations, product is disjoint union. And a monomorphism will actually be a relation that's an injective function. No, not function necessarily. It could be a partial function, yeah. So, but of course, injective partial function means just taking a piece of this, right? Now, if I've got a piece of that, that's my R, that contains all of this piece and all of the other piece as well, then it must be the whole thing. If it contains the left side, if a piece of the disjoint union contains entirely the left side, that would be the factorization of iota 1.
Yeah.
If it contains entirely the left side, it contains entirely the right side, then it must contain the whole thing. That would be R being an isomorphism.
Yeah.
Do you see that, Alexander?
Yeah.
I see surging to the injected, but
Well, remember this was mono,
oh yeah. Okay.
so it was injected from the start. So conceptually, it is the idea that in the product, the two pieces, the A and the B, kind of fill the whole thing.
Oh yeah.
Which holds for disjoint union quite obviously, geometrically, and also for monoids because of that unital property of decomposing elements this way. So the general idea behind this is that intuition behind this concept is that intuition behind the concept of the unital property is that A cross B is saturated by A and B.
So what if we relax that a little bit and just say that there is a monomorphism from the product into either respective part? I know that's always true. Yeah, that's always true.
You wanted to say there is a monomorphism from where to where?
No, from A cross B into A and into B. That's just the prediction.
You mean the project? These are not monomorphisms, though.
Oh yeah, you're right. Okay, so if we just ask that there is a monomorphism from the product into A and into B, because we've now constructed a
There isn't a monomorphism from A cross B to A. For sets and relations there is, but not for monoids. There isn't a monomorphism
sorry,
this way.
there's not a monomorphism, but yeah, okay, that's like a partial.
Well, yeah,
Yeah.
but that's very specific to
Yeah.
sets and relations. Okay, so for answering the first question, we don't have enough time to answer that question. I'm going to only tell you. I'm not going to take you through the exploration of the answer. I'm just going to tell you the answer, what the answer is. There is a very important property of a morphism to be a co-kernel of something. And recall the notion of regular epimorphism from the previous lecture, which was a co-equalizer of two maps. So regular epis, which are co-equalizers, are abstraction of surjective homomorphisms. The abstraction of surjectivity in algebra. It doesn't work for topology. Surjectivity in topology is something slightly different. Not every surjective continuous map will be a regular epimorphism because the codomain could have much poorer topology than the one that's forced by co-equalizer. But in algebra, it works that regular epimorphisms are nice counterparts of surjective homomorphisms from algebra. Now, had every regular epi been a co-kernel of something, we would get a situation which abstracts the idea of a congruence being uniquely determined by the equivalence class of 0, by the equivalence class of 0. And that's because you've got your congruence and you've got your corresponding quotient map.
Yeah.
And now you're saying that this quotient map is universal, is a co-kernel, so it means that it's co-kernel of its kernel, and its kernel will be exactly the 0 class. And the universal property of being co-kernel of its kernel turns out to exactly correspond to the fact that the congruence I started with is uniquely determined by its equivalence class of 0. So it's a very important property if it turns out that all regular epimorphisms are co-kernels. In fact, a regular category, and remember we talked about regular categories last time, a regular category in which a pointed regular category in which every regular epi is a co-kernel is called a normal category. That's how important this property is. And by the way, the name normal category comes from one of my papers. It's a recent terminology. Now, the property we established today wasn't quite normality. We didn't say that every regular epimorphism is a co-kernel. Only some of them. Because these product projections, they are still regular epimorphisms. It's something that can be proven because of the fact that they have a section, this right inverse, the equality we used. This will imply that actually pi2 is a regular epimorphism. And now we're asking it to be co-kernel of its kernel, which, as I said before, is equivalent to saying that it is a co-kernel of some random map. And so basically, what we've proven with this property is that although not every regular epimorphism is a co-kernel, the product projections still are. In the category of monoids, not every regular epimorphism is a co-kernel.
So what are some examples of normal categories?
An example of a regular epimorphism that's not a co-kernel is, if I'm not mistaken, addition of commutative monoid. This is a regular epi in the category of monoids, which is not a co-kernel. How do we say it's not a co-kernel? What is the kernel of this map? Pairs that add to 0, pairs of numbers that add to 0. It's just one such pair. If this was a co-kernel of being one such pair, it means that the kernel is domain 0 object. If this was a co-kernel, this would have been isomorphism. Why would this have been isomorphism? Because if you take 0 map, right, its co-kernel would be co-equalizer of 0 map and another 0 map, and that they're the same 0 map, so the co-equalizer is the same, is just the identity morphism. So if this was a co-kernel, this would have been isomorphism. And of course, it's not an isomorphism because, for instance, as we know, 2 plus 3 equals 3 plus 2, which this shows that plus is not an iso, since 2 elements here are mapped to the same element there. So we don't expect in the category of monoids every regular. We don't expect the category of monoids to be a normal category, because not every regular morph is a cokernel. So it's kind of surprising that some of them are, and it's really nice that the product projections are, because they're very important regular morphisms. And coming back to these examples, this category is not normal. This category, no, the category of groups is normal. The category of abelian groups is also normal. Vector space is also normal. And modules is also normal. That's why in the study of vector spaces, we don't study congruences, we rather study subspaces, because cautioning out by congruence is the same as cautioning out by the kernel. Same for abelian groups, same for groups. But if one wants to develop a theory of monoids, then one ends up considering congruence is not just zero classes.
So the category of abelian groups can be seen to be normal just because the category of groups are right. It's a subcategory.
Yeah. It's a subcategory, although coequalizers here, cokernels here, are not computed the same way as there. But actually, no, they are. Sorry, never mind. It's closed under cokernels. Is the category of sets and relations normal? It's highly not normal. Highly not normal. Why isn't it normal? Because the kernel is always empty there. You don't expect the surjective relation to be universally determined by empty thing. The kernel is empty because zero maps are empty. So as I said, I didn't have a chance to say all the details. Just
Wait,
to
functions, is the kernel in relations also empty?
No, well, in the category. So, what's your question? Sorry.
So, in the category of sets and functions,
there we don't have a notion of a kernel because the category is not pointed.
Okay.
But if we take pointed sets, there is no longer empty, but this category is still not normal. Of course, we know it's not normal because we already said this doesn't have even that property, so it can't be normal. Okay, now in conclusion, I kind of deliberately wanted to show you something that links up with not just research in category theory. I mean, it's a very specific type of research dealing with algebraic structures. But also it links up with my own research in category. In fact, my first paper in category theory, which I wrote when I was, my first paper ever in mathematics, which I wrote when I was a master's student, was to study, introduce and study this property in general categories. And one of the things I proved there was this argument that unital categories have these normal projections. And then I observed that there are other algebraic reasons why we could have this kind of argument. Unital is not the only one. Also, you could have a setup where you've got some kind of implication operation that satisfies x implies x equals 1, and x implies 1 equals x, which if you reverse is a generalization of, if you reverse and denote 1 by 0, is a generalization of subtraction. Sorry, I meant to say here 1 implies x. If I reverse this and denote 1 by 0, I get subtraction. So if you've got this subtraction type of scenario in an algebraic context, you can still carry out this kind of argument. And so when I discovered, and indeed in the literature, I could see that somebody has studied algebraic structures with a subtraction. And then my next question was, okay, but what is the categorical property of subtraction? Because I mean, for this unital property, this is the well-known unital category. But what about the subtraction? And it turned out that nobody had introduced that yet. So I introduced it and I call it subtractive category. So that was
what
my.
is the property? It's very complicated.
No, it's not complicated. It's similar to this one. It says that if you've got R through which iota 1 factors, well, first of all, we need to put the same object here in A. If we've got R through which iota 1 factors, so elements of the form A0 are there, and diagonal factors, so elements of the form AA are there, then by subtraction, we can get elements of the form 0A. So if iota 1 factors, diagonal factors, then iota 2 factors. Yeah, so if elements A0 are there, elements AA are there, and we could have subtracted A0 from AA to get 0A.
Okay, yeah.
The algebraic proof involving subtraction is a bit more complicated than this. It has more steps than this one. The additive situation is easier. Okay, great. So this ends the lecture. If any one of you has any questions, we can talk about them. Otherwise, we'll stop here.
It might be a silly question, but if you like quotient our product with, I think A instead, how does symmetry here apply, so to say?
You mean B? If we quotient out by B?
Yep.
Yeah.
So what's the difference between quotienting it by A and quotienting it by B?
So if we quotient by B, we will get A. And this is because A cross B is isomorphic to B cross A. So that isomorphism will allow me to reduce this to that.
Ah, all right. We can just interchange as A and B.
Yeah.
Okay.
In fact, I recently, no, not recently, sorry, already then, at least in my PhD, not in the first paper, in my PhD thesis, I proved the result that if I require in a category X cross X quotient by X to be X, this is already sufficient, thanks to equalizers and pullbacks, to prove this more general case.
So if you have like more than two terms, you have like A cross B cross C, etc., finitely many, and you quotient out by finitely many but less, you then just get like this. It's sort of
Yes, it still works because I can reorganize this way and apply the previous result. However, you might ask something else, which is in the spirit of what both of you already asked, but what would be the real question, which does not reduce to this one, but it would be similar.
if you have a sum, is it?
Well, some and quotient don't like each other, right?
Well, you could use the splitting up thing, right? Like for normal, if you replace that middle product with the sum, does that?
But we want something that for numbers would be correct, yeah.
But it is correct for numbers.
Okay, well, what are you suggesting?
So A plus B quotiented with C is A quotiented with C plus B quotiented with C.
Okay, good. Yeah, very good. This one is good. One could ask this question, and one could also ask all sorts of other such questions where one comes up with other identities. That, for example, A times B, quotient by B, then quotient by A. Do we get the same as 1? Right? We can write a lot of.
Is quotient associative?
Don't think so. Like the numbers.
Yeah. Okay.
So one can ask all sorts of questions like this, right? We can come up with, invent these formulas and then do exactly the same as we did here. First, describe in which algebraic scenarios this hold. By the way, in my paper that I mentioned, I characterized all algebraic categories in which that property holds. They're a very complicated system of equations that is much more general than just unital and subtractive situations. So the first thing is just to understand algebraically when it holds. And the second step is to extract a categorical property that makes it fall, and actually to characterize the property exactly. This is still an open area of research. So if any one of you is interested for us to explore one of these properties, we can do that. By the way, I'm giving a talk at the Congress of the South African Mathematical Society in December, where I'm going to present nullable categories, which are generalizations of unital categories that come from one of these formulas. And that's a joint work with Michael Wolfnachel. He's a colleague of mine, actually a former student of mine.
I remember like a few weeks ago, we had a session, no, a few months ago, we had that undergrad, where we had like a session where everyone presented their work, and I think he asked that question, but some.
Ah, okay. Yes, he does work with these kind of things. So him and I, we started working on this project to classify all sorts of equations like this, and we easily figured out that it's a very hard project. You have to deal separately with each of the isomorphisms. And we've been able to fully understand one of them, and that will be the topic of my presentation. But there are many others which could be understood much better than we are able to so far. So if you're interested in this, let us know, and we'll get you involved on that research project.
So is this, are you guys looking at this specifically in normal categories? So like extensions of the first quotient rule, or working in reverse, asking when does this hold?
So first of all, formulating the property. I mean,
Okay.
already here we needed to understand what does this actually mean, and we agree that it means that pi2 is a co-kernel.
Okay.
So first is to formulate the property, and then to relate it to other things. Like, for instance, it turns out that this nullable property will be a consequence of this. It will be even weaker than this. So this is weaker than unital, and that will be even weaker than this. And secondly is to find various characterizations and examples and counterexamples that will distinguish it from other isomorphisms. So the overall goal of this project is to classify these isomorphisms for general point and categories in terms of which are stronger, which apply others, and so on.
It would be quite interesting if you get this far enough, and you because you also have like 2a that you can just sum a with itself, right? A squared, so you could, like, if you get far enough with this, you could start doing number, or like applying number theory results to.
Sure. You could try to characterize categories where
Arithmetic holds, yeah.
where things like this hold, right?
Yeah.
Okay, this is the end of this formal course. It was the course offered under NITheCS, specifically under South African Theory and Computation School, and I would like to thank them for the opportunity of for me to offer the course. I would have never had the idea to offer this course, should not have been offered to them. And thank you everyone who participated, and those also who participate in the future by watching the videos. And anyone who is watching these videos is very welcome to contact me if you have any questions. Thank you, Alexander. Thank you, Carlisle, everyone else.
Thank you as well. That was really, really interesting. I got new bunch of ideas, I think, in use. So that was kind of cool, especially topological groups, general group objects.
Fantastic. It was very great that you joined.